This presentation is about the biomechanical analysis of ball velocity. The biomechanical goal of ball velocity. As shown, we have the deterministic model on the right, with tennis serve velocity leading to racket velocity, then to arm velocity, which branches out into three things, with arm torque, which correlates down to shoulder movement of inertia, and shoulder angular velocity. The next section is lateral trunk flexion, which is influenced from trunk torque. And the last one is arm length, which is influenced from shoulder rotation, elbow extension, and then greater racket height. The biomechanical goal of creating maximum ball velocity in the tennis serve is to efficiently and effectively transfer kinetic energy. This is transferred through the coordinated kinetic chain, transferring force through the body, creating maximal racket velocity when hitting the ball at impact. This will be identified through critical qualitative features such as trunk rotation when the body fully extends, as well as through quantitative features such as wrist angular velocity, elbow angular velocity, and racket force velocity. The kinetic chain sequence and qualitative data. In order to achieve the goal of maximum ball velocity, the kinetic chain sequence must be efficient and effective. The trunk allows the summation and transfer of angular momentum from the torso to the upper limb. When rotating the trunk, it can preload muscles from the stretched Sawney cycles, storing elastic energy that can be used as explosive power. Trunk rotation also creates a greater mechanical advantage, allowing you to extend your arms further. This mechanical advantage is also created from full body extension, which maximizes vertical and horizontal linear motion. Qualitative analysis of full body extension lengthens your levers, further increasing distance and time to accelerate. It also incorporates larger muscles such as legs, back, and abdominal muscles to contribute to force through rotational force generation. While quantitative features such as wrist angular velocity directly impacts racket head linear speed and ball velocity. The faster the tennis racket head is moving, the more kinetic energy that can be delivered to the ball. Conjointly, elbow angular velocity is also important. As the elbow extends, it increases racket velocity. The faster the elbow can extend, the greater the angular velocity is. Elbow angular velocity serves in the acceleration phase, transferring energy from the shoulder and accelerating the forearm and racket, minimizing racket head speed. The racket's linear velocity is directly transferred to the ball on contact and will determine the tennis ball's velocity. These are some important considerations to film. Camera angle and position to ensure the motion of interest is captured in the appropriate plane and distance. The camera was positioned at 90 degrees to record a full body image and arm swing of the racket. With camera height aligning with the center of the movement, lighting is also another important factor, as adequate and uniform lighting prevents shadows, glare, and improves the ability of motion sensors to capture joint movements, thus making angular velocities calculations easier. A plain white background was used, making it highly contrasted and compared to the participant. A slow motion video using 240 frames per second allowed for precise measurements, such as angles of joints. This ensured specific movements could be captured frame by frame, minimizing blur and improving temporal resolution, ensuring accurate kinematic measurements. Ensuring clear instruction on the movement and follow-through phases and allowing for warm-up ensures the subject can forcefully perform the tennis serve, preparing the subject with contrasting tight clothes, as well as making markers clearly visible and accurately throughout all phases of the movements. This is especially important as markers define the joint centers and be placed in a stable position. Markers were placed specifically on the shoulder, acromion process, elbow, lateral epicoidal, wrist, radial and ulnar styloid process, and the racket on the grommet. Ensuring the right racket and tennis ball is used, it is also crucial that they directly determine how forces, motion, and energy transfer occurs through the kinetic chain. This is elbow and wrist angular velocities. Greater levels of velocity amongst wrist and elbow correlating to the increased tennis ball velocity. The results presented, seen in the graphs, saw elbow angular velocity peak roughly 50% through the serve, with peak angular velocity of 350 degrees per second, compared to a study from Andre Brito and co., where Group A greater than than average ball velocity presented a maximum of 330 degrees per second, also 50% through the serve. In the same experiment, they also found that Group A had significantly greater elbow velocity compared to Group B, thus displaying a positive relationship between elbow angular velocity and ball velocity. They also found Group A had higher levels of wrist angular velocity. Our experiment displayed peak wrist angular velocities of 335 degrees per second as shown in the graph, roughly 40 to 50% through the serve, thus highlighting the fundamental contribution of elbow extension and wrist flexion has on ball velocity, as supported from a meta-analysis where the speed and the range of the wrist angle flexion effectively increases the speed of the racket, thus increasing ball speed. However, they found amongst the advanced group, elbow abduction and adduction angle didn't directly correlate to an increase in ball speed. Conversely, the meta-analysis found the speed of elbow abduction and adduction increased amongst the advanced group. In this experiment, as shown in the graph, elbow angular acceleration reached a peak value of 2,225 degrees a second, roughly 30 to 40% through the serve, with wrist angular acceleration reaching peak flexion of 2,100 degrees per second, roughly 60% through the serve. Greater elbow and wrist extension contributes to the forward drive of the racket, increasing racket velocity. As shown in these graphs, total elbow displacement peaked at 183 degrees, roughly 50% through the serve, while wrist total displacement peaked at 90 degrees, roughly 40% through the serve. A systematic review from Lamprich and Co. reported significant larger angular displacements for elbow and wrist, which correlated to greater wrist, elbow, and racket velocities across these studies. Wrist and elbow displacement can contribute significantly to racket velocity. However, the timing of extension and flexion in the kinetic chain is more important for ball velocity. These are the 5 phases of the tennis serve, with phase 1, ball toss, phase 2, acceleration phase 3, racket to ball contact, phase 4 was full extension, and phase 5 was the follow through. Changes to elbow angular displacement. A meta-analysis on biomechanical changes found significantly higher level velocities of racket head, shoulder, and elbow came from horizontal flexion, abduction, as well as internal rotation and impact of horizontal direction during the serve. Even though shoulder angular displacement or velocity wasn't recorded, elbow angular displacement was recorded, reaching roughly 180 degrees. The displacement for normal elbow joint is usually around 150 degrees. As supported from Gross and Co., found the fast tennis serve has dominated the elbow flexion. They further found that the maximal ball velocity has been reported with elbow flexion close to 30 degrees from maximal extension at ball impact. The slightly flexed elbow creates a mechanical advantage for medial rotation of the shoulder, thus further increasing racket velocity. Compared to our study, our participant's elbow was fully extended to 180 degrees. It is conclusive from this evidence that participants should have their elbow flexed 30 degrees more to maximize ball velocity during the serve. This is changes to wrist extension. The participant's wrist angle was also not optimal, as during the ball impact phase, he had a wrist extension angle of 52 degrees. Optimal point of contact for wrist extension was 15 plus or minus 8 degrees for maximal ball velocity, as found in the study. If the participant decreased wrist extension at the ball impact phase, it would create a greater angular velocity at the point of contact. This is due to time during the release, loading, cocking, and acceleration phases increasing, creating greater angular velocity as linear motion increases. Changing racket angle and ball placement. It was quantitatively noticed that during the ball impact stage of the tennis racket was driving up and the ball was sitting on the lower third of the racket, while a study found that the racket should be in a downward motion, with the ball impact on the top third of the racket. If the participant at the time of the ball impact had a downward motion of the racket with a ball contact of the upper third of the racket, this would significantly increase ball velocity as racket velocity will be maximized as it will no longer be accelerating. These improvements are recommended to maximize ball velocity. This is the first page of references and the second page of references.